Professor, maybe we can start.
Hello. Yeah. So should we start?
Yeah.
Okay. So yeah, so first of all, thank you for giving this opportunity to present this class. I believe that people will trickle in to this class. So we have a 2-hour session for discussing about this topic on fault attacks. So the idea being that we will start with this, and we start with the theory behind fault analysis. And in around 1 hour of time, we will try to give you a live demonstration of fault attacks by Siddhartha, who is also there on this call. And then we will continue to discuss about some advanced topics on fault analysis. And in between, if there are any questions, then please feel free to stop and ask. We will try to keep the discussion as interactive as possible. So, we start with this saying is, like one man's fault is another man's lesson. So the idea being in the context of cryptographic algorithms, and in particular, like when you try to implement cryptographic algorithms on systems, what are the, like threats that, like arise from faults or faulty computations is what we will try to cover in our discussion. So to start with, we have, we'll try to kind of introduce this topic of fault attacks. And before I get into cryptographic algorithms and fault attacks in that context, I would try to kind of first, motivate that the impact of faults essentially has become even more when you try to look at, various aspects like neural networks, cloud servers, automotives, post-quantum algorithms, apart from, of course, like the conventional crypto algorithms like symmetric key and public key algorithms. So for instance, right, when I talk about fault injections in the context of neural networks, it is now a widely kind of studied topic to see, like if there are, like certain neural network accelerators which are running on some target devices, and there are fault injections trying to pot up the weights of the neural networks, how does the inferences vary? So likewise, right, when you talk about automotive systems, we essentially often see that because of faults, certain vital computations or security checks or even safety checks can get bypassed. So therefore, right, faults essentially have become growingly important in the context of not only crypto algorithms, but in general security. However, for this discussion, we shall try to kind of more focus on crypto algorithms. And one of the reasons why this essentially has become more popular is because of the fact that the various injection techniques of faults essentially have become cheaper and they have become more accurate. So for example, in this slide, you see some pictures of fault injection methodologies being done by maybe some low-cost injection techniques like clock glitches, voltage glitches, to something more fancy like using electromagnetic guns, to something even more costlier, say using laser-based techniques. Recently, there also has been some very interesting works which are called as row hammers, which tries to exploit the reliability issues of DRAM chips and show how faults can be injected in your memories, which can correspondingly affect not only hardware designs, but also the software codes or software ciphers which are working on those memory elements. And therefore, faults essentially has become more and more popular and more important field of study in the context of security. So let us start from probably, like the first, I would say, pedagogical example of where faults were utilized for crypto algorithms. And we start with this paper from Dan Monet and his colleagues in Eurocrypt in '97, where they talk about how faults can be, utilized to recover the key of RSA like crypto systems. So like for the uninitiated, RSA essentially is a public key algorithm, and you can essentially use the RSA algorithm for, encrypting as well as for decrypting. So in particular, let us consider maybe a hardware chip or maybe some kind of, target device on which RSA essentially decryption has been implemented. And imagine that the secret key is stored in some kind of memory inside the chip. Now this memory or the secret key, if I denote it by say the decryption key D, so now what I am like interested is is to recover this value of the secret. So imagine that this is my secret key, and I would be essentially trying to see how faults can be used to recover this secret key value. So for this, let us quickly recapitulate about how the RSA decryption works. So at a very top level, it basically does this, that is, it takes maybe the cipher. So in this case, let us denote the cipher as S. And what it does is basically it takes S and raises it to some exponent, say D. And then it does a modulo operation. So the modulo is often done with a public, like parameter, say modulo n, and obtains the message. So now, so this is the very standard, like textbook definition of RSA, decryption. And we would try to see how essentially D can be recovered because of the influence of faults. So to begin with, let us try to see that what is the consequence of a fault. So imagine that because of, maybe some kind of, one of these techniques that we were just now seeing figures at or pictures at, we try to kind of induce a fault, and because of which, imagine that one of the bits in the, memory gets corrupted. For example, it may be the ith bit of your secret key exponents gets flipped. For example, DI, if I denote DI for the ith bit of the decryption exponent, it becomes, complemented because of the fault. It gets flipped. So now, when you do an RSA decryption, you will be essentially taking this same S, and you will be performing a decryption with, say, D hat. Okay, so D hat denotes to be the faulty value of the decryption exponent, and you do again this modulo n computation to get the faulty output, which is M hat. So now you can observe that, or what this paper showed, is that if you have got M and M hat, and if you find out the ratio between M hat and M, that means you calculate, say, M hat and divide it by M, then it is not very difficult to see that because of this, certain very interesting thing will happen. So you can observe that if I, for example, take D and observe or write down the binary exponent of D, then D stands for nothing but, if it is a, say, like an n bit or a t bit vector, then that would imply that it is, say, 2 to the power of t minus 1 dt minus 1. Imagine that, like the decryption bits are denoted as, say, dt minus 1 to, say, like d0. So it is a t bit vector used to denote the, like bits of the decryption exponent. Then that would mean that d is equal to 2 to the power of t minus 1 dt minus 1 plus so on till, like 2 to the power of I di plus like this till d0. Now, because of the fault, what happens is the decryption, if I denote it, the faulty exponent as d hat, then everything remains the same, okay, except the ith bit, which gets flipped. And because of which, right, since the ith bit gets flipped, the others does not change. If I consider this ratio, that is M hat by M, which is the, the ratio of the faulty plain text and divided by the correct plain text, then it is not very difficult to see that every term, will get cancelled out, save the ith bit. So only the ith bit will not get cancelled. And therefore, right, we will be remained with, like this kind of equation where you are essentially, it becomes only conditioned on the ith bit. And you can essentially think that if this di, because this di can be, can take only two possible values, it can either be a 0 or it can be either be a 1. And therefore, right, if di is equal to 0, then the ratio of M hat and M will be equal to S power of 2 power of I, of course, modulo n. And if di is equal to 1, right, then it will be the reciprocal of that. And you can observe that since as an attacker, you already have the value of S, you can essentially try all possible values of I, and you can check that whether one of them essentially gets satisfied. So that is exactly what is the idea behind the attack. And you can essentially observe that because of this, one can, like apply this to, like obtain the secret key or the ith bit. So this is the working out of this attack, and you can observe that that this can be applied on the Aes algorithm. So what I mean is shown here by a very simple example. So suppose let's consider a very small pedagogical example. Of course, these are small parameters and not necessarily the actual RSA parameters, but hopefully with this we can understand the exposition. So what I mean is that suppose your public key exponent is 7 and your n is 77, which is your public key exponent, and imagine that your secret key is d, which is equal to 43. Okay, so this is your secret key exponent, and that if you expand in the form of the binary values just shown over here. Now, if you perform the correct decryption with say a ciphertext shown as 37, you can check that the plain text will be provided by as 9 if there is no fault injection. However, if there is a bit that gets flipped, you get a wrong output, which is 67. And by the previous technique, you can take the ratio and you can check the two possibilities, whether the ratio of m hat and m is equal to s power of 2 power of I, or is the reciprocal of that. And based upon that, you can essentially arrive at the fact that I equal to 3 and the corresponding key bit exponent is d3. So now this means that this is a very simple example to illustrate that the ability to inject faults inside the secret key exponent not only has an impact on fault tolerance, because of course you are getting a wrong computation, and if you are naively we will think that we can imagine that the effect of the fault is only limited to the decryption and I can just repeat the decryption and I can go ahead. But this simple example tells us that the cost is even more, or the implication is even more, because it shows that your key bits are getting leaked because of the fault. And that is why, essentially this study becomes so important, not only on fault tolerance, but also on the impact on security of crypto systems. So this example has been taken from this book by Koren and Krishna, and you can essentially refer to this textbook as well for more details. So later on, researchers tried to apply it for symmetric key ciphers. So by symmetric key ciphers, I mean those category of ciphers where the recipient and the sender both share the secret key. So our old DES is an example of symmetric key cipher, and nowadays we have got the famous Advanced Encryption Standard, or AES, which is an example of a worldwide standard algorithm for symmetric key ciphers. So in this original paper by Beham and Shamir in Crypto 97, that is almost the same year as that of the Bonet's Eurocrypt paper, it was mentioned that the original algorithms that were used to attack the RSA algorithms do not straightforward extend to symmetric key ciphers. And one of the reasons was the fact that symmetric key ciphers typically do not have a very algebraic structure. They are often based on properties which are essentially based on complex bit manipulations, and it is not often adhering to a specific algebraic operation. In particular, the DES algorithm was an ideal example of such kind of block cipher, which was also a standard at that time for symmetric key ciphers. So therefore, we need original ideas of how we can perform fault attacks or fault analysis for symmetric key ciphers. So these category of blocks of analysis technique which were developed for symmetric key ciphers were abbreviated as DFA. So DFA stands for Differential Fault Analysis. So this I will elaborate subsequently. So in order to understand the idea of differential fault analysis, let us take the example of AES, which is nowadays a standard for symmetric key block ciphers. So just to quickly recapitulate how the AES structure works, let us take an example of in particular the most prevalent standard of AES, which is called as AES 128. So in AES 128, you can imagine that there is this there is a plain text. So the plain text, so I will take the example of AES 128, but it can be also extended for other parameters of AES. So in particular, AES 128 has got a plain text of dimension 128 bits and also has the round keys of dimension 128 bits. So the first thing that is done in this context is, like you take the plain text and you need to kind of store it in some form. And that form is often called as a state matrix. So what you do is you take the AES 128 bits and you organize them as a 4x4 matrix of, like where every element is a byte. So for example, you can see there are 60 elements in this matrix. Each of them correspond to a byte. So this is your plain text. The key is also of the same form, which is you can think of them as to be a 4x4 matrix where every element is a byte in this matrix. And the first thing that you do is an XOR, which is essentially called here as, or referred to here as the add round key. So this is essentially standing for the exclusive OR operation that you are doing between the plain text and the 128-bit key. And then you pass it through a sequence of layers, which are called as sub-bytes, which is nothing but an array of S boxes or substitution boxes, which are nothing but substitutions which are done at the byte-wise level. And then there are these two operations which are called as shift row and mixed columns. And then finally, you have got another add round key, which is done after every round operation. So this you kind of repeat it 9 times in the context of AES 128. And finally, there is a, like a final round where you just do a sub byte and a shift rows and you do an add round key to result in the final ciphertext. So this is how any standard AES 128 algorithm would be implemented. And if you look down into the cipher, you will probably look this kind of, like implementation being done on the hardware or any, it could be an FPGA design, it could be an ASIC design, or it could be maybe an, like a design that you have done on an embedded platform. So you can observe that the internal layers that are there, which are, like the combination of byte substitution, shift rows, and mixed columns, this has been done with a lot of care. Okay. And the objective is that the attacker wants to kind of, wants to obtain the secret key, but the designer wants to abate the attacker from obtaining the secret key because the entire algorithm is known to the public by the theory of what is called as the Karskov's principle. And the attacker, what it doesn't know is only the secret key. So now we will see that assuming that the classical AES algorithm is kind of secure against conventional cryptanalysis techniques, but how we can utilize faults to obtain the secret key. So in order to understand that, first let us try to take a look at what is the effect on error on AES. If you look at that, we'll probably get an idea about how, like nicely the AES algorithm has been designed. So first we see, like some plain text ciphertext pairs. Again, these are taken from this Koren and Krishna's book. You can see here that we show you some examples of plain text and, like the corresponding 128-bit key and a ciphertext. And we make a single bit error, as you can see here, to the plain text. And likewise, a single bit error has been done in the key. Now you can observe that the ciphertext that you obtain in this case and the ciphertext that you had obtained previously. So if I call this as the correct ciphertext C, and maybe this is the, like the erroneous ciphertext C star, you see a complete change. Okay, it completely looks arbitrary compared to C. So likewise, even if there is a single bit change in the key, that also results in a totally scrambled output. So this shows how, like sensitive the AES algorithms or, like a good cipher is towards error. But then the question is, right, can we exploit this error? So that is what we will try to, learn. So in order to do that, let us try to see what, like how a DFA would typically look like. DFA stands, as I mentioned, about differential fault analysis. So it is a fault analysis which tries to exploit differentials. So differentials essentially mean that, like typically in the context of cryptanalysis, we often say, like it is a difference of two states. Like, for example, if I take a plain text P and if I make, for example, a change in the plain text P by some few bits, and I call that as P dash, then often I will refer to the XOR of P and P dash, basically to measure the difference between P and P dash as a differential. So now what we do here is in the context of AES, we keep the same plain text and we obtain what is called as a fault-free cipher. And in another run of the encryption, we take the same plain text, but while doing the encryption, we make a change in the environment. We probably, like create a clock glitch, we make a voltage fluctuation, or we use kind of, like electromagnetic guns or maybe a laser station to induce or inject a fault. And because of this, we get a faulty cipher. So you can imagine that I have this correct cipher and I have now a faulty cipher, which I called as C star. And now I find out the differential between these faults. That means I calculate the differential or difference by computing the XOR between C and C star. So this essentially by our definition is called as the differential of the faulty outputs. And then that we subject to certain analysis, which is called as differential fault analysis. So in practical terms, if you want to do a DFA, here is an illustration of how you can do it by a very simple setup. So what you can do is you can probably take an FPGA. In this case, the board that we show is a very standard board, which is called as a Sakura. So this is a Japanese board, and likewise there could be other targets that you can also fits in. And we have got an AES which has been implemented on the corresponding FPGA that is running on this board. And here is an illustration of how the circuit looks like. And what we do is we have got an internal clock generator. So we essentially use a normal clock. So this is called as the clock slow, which is the slower clock at which your circuit has been designed. And now at a certain opportune time, which you want to kind of control as an attacker, you essentially pass a fast clock. The objective being to switch from the slow clock to the fast clock is to essentially create a glitch in the clock. And likewise, right, this glitch in the clock is expected to create some kind of internal faults inside the computation. You can do, equivalently certain injections also by perturbing the voltage line. And likewise, you can also think about an EM gun and laser stations and so on. But this can be a very simple setup to understand how the fault patterns look like. You can also use, internal logic analyzers like ChipScope to observe the fault patterns that occur inside your circuit. So now the question is how we can exploit them. So in literature, you will find that there are different types of differential fault analysis. The attacks can target the data path of AES. It can target the AES key schedule. So when I say, it can target the data path, it means that the faults can occur in the AES data path. That means, as I mentioned that this is your, block cipher structure. So this is typically what is called as a data path. So you can see here that if I take the input and from there, the cipher has been obtained. So this transformation is called as a data path of the cipher. On the other hand, you observe that in the original definition of AES, you also need a round key for every round of your encryption. So now this round key, you need to obtain from your main key, which is the secret primary key. So in order to do that, for example, in AES 128, you have 10 rounds of encryption. So you need to create 10, internal round keys. And these round keys are obtained by an algorithm, which is called as the key scheduling algorithm. So now some attackers would try to kind of target these paths, which are called as the data path. And some attackers can also try to target the key scheduling algorithm. In our discussion, we'll be largely focusing on data path faults. So therefore, you can target the data path faults, which are essentially faults which occur in the AES data path, or you can also target the AES key scheduling algorithm, which basically creates a fault in the AES, the algorithm which generates the round keys from the primary keys. Likewise, you can also create a definition of faults or fault attacks by the underlying model. For example, you can assume that the faults are pertaining to single byte faults or multiple byte faults. So by single byte faults, I mean that, remember the state matrix depiction that I told about the AES algorithm. If you assume, for example, the fault is kind of restricted to a byte, okay, and the fault can be any value. It can be any random fault that occurs inside the byte, but it kind of is restricted to a byte. Then we call that as a single byte fault model. On the other hand, the faults can also spread to multiple bytes, and in that case, that fault model we called as a multiple byte fault model. So now let us try to analyze the AES 128 algorithm with respect to a byte fault model. So that means assume that there is a fault that has occurred because of maybe the variation in the clock glitch, and because of that, there is a random fault that occurs at a certain instance of the encryption process. So in the context of AES 128. Our sweetest spot to inject the fault is at the input of the 8th round of the encryption process. So remember that AES 128 has 10 rounds, and we inject the fault at the input of the 8th round, and that essentially kind of also propagates through the cipher. So what happens subsequently because of the byte sub, this is the, as I mentioned, is the byte by byte substitution that you do. This fault gets maybe transformed into some other unknown faults. And likewise, right, the fault propagates. Now there is a specific layer which is called as a mixed column. So mixed column essentially, as mentioned over here, is a specific transformation that is done inside the ciphering operation to produce what is called as a diffusion in the cipher. So how the mixed column is essentially implemented, you can see here that if you take any standard textbook of AES, you can see that the implementation has been done by essentially like pre-multiplying each of these columns. As the name suggests, it's a mixed column algorithm. So it takes this column of the state matrix and it multiplies it by a fixed matrix. Okay, so the matrix typically has got values as I mentioned here as like 2, 3, 1, 1. So this is the hard-coded matrix which has already been designed by the designers of the Aes algorithm. Okay, so now these elements, okay, essentially as shown here 2, 3, 1, 1, essentially are not integer values. Okay, so they are implemented using certain specific finite field operation, which at this point you can I would just like to mention that this is technically called as the Galois field. Okay, so this is often called as the Galois field, which is GF2 power of 8. So therefore, what happens is now these column elements, these are also Galois field elements, and you can just think of this at this point in this manner. That is, it basically does a usual multiplication of the elements with the corresponding elements of the mixed column matrix. But since this is a field element, you essentially always try to ensure that the results are also inside the field. So without going into too much details, actually what you can observe here is that if I take this matrix element and if I multiply with this particular column, in this case, this is the difference that you observe here, shown here as f dash, and likewise there is no difference at this point, and likewise at these 3 bytes, then you will find that the faults start to manifest certain interesting patterns. For example, you can observe that now in this column, if you observe, note that this is a 32-bit column because there are 4 bytes and each of them correspond to a 1 byte. The number of possibilities that can occur here is determined by the value of f dash. Okay, so now this f dash being a byte, it can take 2 to the power of 8 values, that is 256, and that would imply that this entire column can only take 2 to the power of 8 values. Okay, so likewise, if we allow this to propagate, we will find that because of the next byte sub, which is again a byte-wise substitution, this will get replaced into some like unknown values, and then this will pass through what is called as a shift row. The shift row essentially is an operation in the Aes algorithm. What it does is basically it takes the first row and does not do anything. The second row, it performs a left shift. That means like this will essentially come to this point. It's a circular left shift that you do by one step, and in the third row you do again a left circular shift now by 2 steps, and in the third row, at last row, you basically do a left circular shift by 3 steps. And if you do this, then you can see that F1 remains in its original position, F2 comes to this position, and F3 and F4 are in these designated positions. And now if we again allow the mixed column to pass, then you can verify that because of this matrix, which is again the same matrix gets also operated at this step, and therefore each of these columns, like you can observe, F1 will essentially get transformed into this column as shown over here, and likewise for the other 3 remaining columns. So now what you can do is, as an attacker, since you are at this point, you can try to guess this last 10th round key, and you can try to work behind and go to this position to go, and work and go towards at this position and check that whether these relations that you have observed, that you have calculated analytically, are really being maintained by your by the guess that you are doing for the key. So what I mean is, you can actually form equations of this nature as shown here. So these equations are nothing but trying to kind of work behind. It basically guesses portions of the key, as you can see here, and it tries to kind of exploit the fact that whether for example, like if you focus on like this particular column, you can what you want to verify is that whether this byte is twice this byte, and that essentially gives you, say, the first equation. Okay, so that gives you this equation. Okay, so you can observe that that gives you this equation, and likewise you can verify that whether that whether this byte is you can verify that whether this byte is same as this byte, and whether this byte is thrice as this byte, and based upon this you can create some equations. Okay, so this essentially gives you these three equations. And now so in this equation, the ISB stands for inverse sub byte, because when you are working behind and you are going from the cipher to this going behind, then you are working behind the S box, and that means that you are computing inverse of the S box. And note that the S box is a bijective layer, and therefore its inverse does exist. So now with this, you can show that, like now at this point, right, you have guessed certain bytes. And if you observe these equations carefully, you will find out that the key bytes that you have guessed here are shown here as K00, K13, and like K22 and K31. Okay, so you need not kind of go into the entire details about this equation at this point, but just keep in mind that there are 4 bytes of keys that you have guessed. So 4 bytes means the total possible complexity would be 2 to the power of 32, because that is 2 to the power of 8 for every byte. And since there are 4 bytes, that corresponds to 2 to the power of 8 power of 4, which is 2 power of 32. But then the question is, on a random basis, right, if you make a guess, how many of them will really satisfy these equations? So you can verify that because of the nature of these equations, the probability that each of these equations will get satisfied, that means if you randomly guess maybe a K00, then the probability that a random choice of K13 will satisfy this equation, you can work out it is 2 to the power of -8, because it's the probability that 2 bytes are randomly equal. So likewise for the second equation, it is also 2 to the power of -8, and likewise for the final equation, the probability is also 2 to the power of -8. So a random choice of the keys that you are doing satisfying these equations has a probability of 2 to the power of -8 power of 3, which is 2 to the power of -24. And since initially we are 2 to the power of 32 possible key guesses, the number of keys that will survive this test, you can, the expected value of the number of keys which will satisfy this test, you can verify it will be a product of 2 to the power of 32 and 2 to the power of -24. And that is nothing but 2 to the power of 8. So therefore, we had started with guessing a byte of the keys, like 4 bytes of the key, and we essentially are left with only 2 to the power of 8 choices for that quartet. And you can see that, and that essentially means that you can essentially reduce and that is only with a single fault. If you have got 2 faults, and if you take, 2 possible choices of these key quartets, and you take an intersection, then with a probability of almost 1, a single fault, a single key will survive. So therefore, one question that at this point you can understand that we have just injected a single fault, which is essentially the fault that we have injected at this point. Okay, this is the fault that we have injected, and because of this fault, the key quartet essentially like one key quartet. So by one key quartet, I mean 4 bytes of the key. Reduces to 2 to the power of 8 possible choices. Now in AES 128, there are 16 bytes because there are 128 bits of the key, and therefore the total complexity, right, is 2 to the power of 8 power of 4, which is equal to 2 to the power of 32. So therefore, you can observe that, So you can observe that at this point, what happens is, because of this operation, the number of possible values per 4 bytes of the key is around 2 to the power of 8. And you can observe that for the entire 128 bits of the AES key, there are only 2 to the power of 32 possible candidates which are possible. Now the question is that can you reduce it further? Interestingly, you can actually reduce it further. Okay, so you can improve upon this attack and show that a single fault can reduce the AES key size to only 2 to the power of 8 values with a single byte fault. And this small complexity of the attack really makes it feasible on a real-life FPGA implementation or any hardware device or any embedded target that you essentially have. So this is a paper that we published way back in 2009, 2011. So if some of you are interested, you can take a deeper look into this paper. I'll try to give a very top level exposition behind this idea of the attack. So what you do over here is, we have already discussed about the first phase of the attack. In the first phase of the attack, we have essentially reduced the key size to the power of 32 possibilities. In the second phase, you try to go ahead further and reduce this key size even smaller to smaller values. So in fact, you will try to reduce the key size to only 2 to the power of 8 possible values. Okay. So, like just to make our discussion a bit interactive, right? I would like to know that if there are any questions till this point. Any queries till this point? Okay, so if not, then let me go ahead. So what I mean to say is that we have essentially been, like trying to kind of exploit the faults. For example, if you go back to this discussion that we had, for instance, this particular illustration. So we have been trying to kind of exploit the faults at this point, okay, based on these state matrices, the state values. Now we would try to kind of go ahead further and try to see that whether the single fault that we had essentially is able to give us some extra information. So in order to understand that, a bit of, like I would say, clumsy mathematics has to be kind of tackled here. We essentially try to kind of exploit an information which is there at the output of the 9th round, or like in particular, we would try to kind of like exploit the faults that are essentially created at this point, which we did not exploit previously. But if you want to exploit these faults, then the attacker needs to work behind this round, which means that it needs to go behind the 9th round. And that essentially kind of involves a bit of nasty mathematics, because you have to kind of also kind of bring the key scheduling algorithm into your equations. So let's take a very quick deep down into this. So what I mean is, at this point, we have been, like traditionally at this point where we have reduced the key size for AES 128 to the power of 32 candidate values. And now we will try to kind of reduce it further by exploiting these equations at this point. So how do we do that? So in order to do that, you essentially observe that these faults or these values here also had this nice faulty pattern as we have seen previously of 2F, F, F, and 3F. So now the question is, right, can we exploit this? So now one can observe that if you want to exploit this, you can indeed do that, but then your differentials will be with respect to the 9th round state. And the 9th round states are shown here by these delta S9s, like as shown over here. And if you want to observe this, you need to express these S9s. Note that these differentials are not directly observable by the attacker. In the previous case, the 10th round differential, the attacker is able to observe because that is observable from the cipher text. But now these 9th round differentials are not observed by the attacker because they are not simply visible to the adversary. So therefore, what you have to do is you have to express these differentials after the 9th round in terms of the 10th round differentials, which is the differential on the ciphers, by using the key scheduling algorithm. So this is what I essentially, like would like to kind of quickly talk about. Of course, like it depends upon, like our time and how much we would like to get in. But what I want to say at a very high level is that we want to kind of exploit the faulty patterns at this point. Okay, so we want to kind of really, like exploit these faulty patterns. So let me, like try to see that whether we are indeed able to kind of understand this part. So note that just to kind of quickly recapitulate about the algorithm of the Aes algorithm, what you're doing is you are essentially passing it through an 8th round XOR, and then you are passing it through a layer of sub-byte and shift row, and that you are following by a mixed column transformation. So now when you're working behind, like previously we had worked through the inverse S box, you need to understand what is the inverse mixed column. And if you take any standard textbook of AES, you will find that this is the definition of inverse mixed column. which is nothing but the inverse of the mixed column matrix that I first showed. Remember that the mixed column matrix that I showed as 2, 3, 1, 1, and so on. So this is the corresponding mixed column. So this is the M, okay? This is nothing but M inverse, and that is referred to as the inverse mixed column, which has got elements like 14, 11, 13, 9, and so on, which are slightly more complicated than the original mixed column matrix elements. So now what you want to do is you essentially try to kind of work behind, and you try to kind of exploit equations of this, by which we try to exploit these faults. So for example, if I assume that these fault values as values like P and P, then this byte essentially takes the value of 2P. So now what I would like to do is I would like to write an equation of this nature where 2P is nothing but the inverse of the S box applied on the fault-free part. So this is the fault-free part of your computation. And this is the corresponding faulty part of your computation. So this is the faulty part of your computation. And you take an XOR or differential between this. So note that when you are calculating this part, you are essentially at this point, because you are, like at this point where you essentially have got the cipher, say the output of this being the cipher text after the 9th round. Let us denote it by C9. And there is an XOR with the key or the 9th round key, and we denote it as K9. So now one can write this C9 in this format. So this is note that the 9th round cipher, and you can, very well, think of that to be another 4x4 matrix, where every element is referred to as some Cij, which stands for the ith row and jth column. So note that there are 4 rows and 4 columns, and therefore we go from C00, C01, C02, C03, and likewise to C, C30 to C33. So this is your 9th round cipher. And likewise, the 9th round key can also be, written down as this 4x4 matrix. So now what we do is we have an XOR between this C9 and the 9th round key. So that is exactly this step, because you are working back. And now this output at this point, we apply this inverse mixed column. So note that the row of the inverse mixed column is shown as 14, 11, 13, and 9. And that is exactly what you kind of multiply with the XOR of C009 and K09, and you multiply it with 14. So like this, you multiply the next element with 11, and finally the next one with 13, and finally with 9. So far so good, but you can observe that these equations are with respect to the 9th round states, and similarly with the 9th round keys. Okay. So now, in order to understand how to express the 9th round keys, so note that you do not know the 9th round keys, but what you have done by your first phase of the attack is you have reduced the possibilities of the 10th round key to the power of 32 possible values. So now what you can do is you can take each of these 2 to the power of 32 keys of the 10th round key, and you can find out what is the corresponding 9th round key corresponding to that, because the AES key scheduling algorithm is a reversible process. So what I mean by that is, if you take the 9th round key as denoted over here, and you can express the corresponding 10th round key by, with respect to the 9th round key by studying the key scheduling algorithm of AES. So let us take a little bit of look at how the algorithm for, for key scheduling looks like. So in particular, if you take the 9th round key of AES, you can, denote it in this manner. For example, I can write down, say, these corresponding elements as K00, K01, K02 and K03. So this stands for the first row of your 9th round key. And likewise, you have got the second row shown as K10, K11, K12, K13. And likewise, you have got K20, K21, K22, and K23. And the final row is shown as K30, K31, and K32, and K33. So these are your 9th round key values. You can also use maybe 9 to indicate that these are 9th round key bytes. So now what you do is, as a part of the key scheduling algorithm, you essentially process this in a manner which is defined in the AES specification to get the 10th round. So now what you do is this, you basically, take the first column of this 9th round key, and you take the 4th column of this 9th round key, and you perform a processing on it to obtain the first column of the 10th round key. So you can observe that what is done here is this particular column, that is the last column, is essentially, like rotated in a cyclic manner, which means that this byte comes up and this byte comes up and this byte comes up and this byte goes down, and you perform an S box on it. And that gives you, and that you XOR with the corresponding first column. So that means that what you do is you take K009 and you XOR it with, say, an S box that you are applying on K139. Okay. And likewise, you repeat this process to obtain, to obtain the first, first column of the 10th round key. So let us, write this as, say, K0 of 10th round to indicate the entire column of this particular 10th round key. So like this, what you do now is you take this column, that means the, the second column of the 9th round key, and you XOR it with K010 to obtain the next column of the 10th round key. That means you get what we can denote as, K110. Okay. So what I mean is that this K110 is nothing but an XOR of K010 XORed with K19. Okay. So therefore, you can easily write down this K19 as an XOR of K110 and K010. Okay. So I'll not go into all the details of the equation, but just leave you with this thought that if you have the 10th round key, then you can do similar kind of operations to obtain the 9th round key. So that means that what we have done in our first phase of the attack, we have reduced the possible values of K10 to only 2 to the power of 32 values. And now I can do a very simple operation on the 10th round key, which means basically I take the 4 columns of the 10th round key and I just start, XORing the corresponding columns. For example, here I XOR the 0th column with the first column, and that gives me one of the columns of the 9th round key. So I just take this one, I XOR it with this one. Likewise, I take this one and I XOR it with this one. And that gives me the corresponding 9th round key. So this is exactly what is done over here. So this is your 9th round key, and that has been expressed using the 10th round keys. And now using this, you can fit into this original equation that we have derived. And you can, substitute the 10th round keys by the 9th round keys. And that will give you a pretty complicated looking equation. But, if you give time, then it should not be difficult to understand what it means. And now what you can do is you can verify that whether so likewise, you can do it for, the first equation, which is 2p. Likewise, you can do it for p, p, and 3p. And therefore, you can obtain 4 sets of equations as shown over here. So I've just written, at this point, not the entire equations, but only the corresponding key bytes, which dictates the values of 2p0. Like 2p0 depends upon certain key bytes. And likewise, the next equation pertaining to p0, certain key bytes depend, and likewise, and so on. And if you do that, then basically what you are doing is this. That is, at this point, you have been able to express these equations by the 10th round keys. And now note that if you randomly, again, remember that the probability that a random choice of these faults satisfying these equations is 2 to the power of -24. And our first phase of the attack gave us with 2 to the power of 32 possible values of the key. And therefore, a single fault reduces the possible keys values to only 2 to the power of 8 values. So this is an expected value of the key space. So that means a single fault injection can reduce the possible key space to an expected 2 to the power of 8 values. So that is the implication of this attack. And in particular, you can see that since you are doing it for all the 2 to the power of 32 keys, if you do it naively, then the time complexity will be proportional to 2 to the power of 32 AES operation. But if you are, if you observe the key schedule, and you can observe very interesting phenomena, which means that you can observe that the second and the third equations, which are shown over here, they essentially do not depend upon 2 key bytes. Okay. And therefore, you can do a nice divide and conquer attack to reduce the keys, the time complexity of this attack further. So what I mean is that in the classic case, what we have studied so far is that you can reduce with a single fault, you can reduce the key size of AES to 2 to the power of 8 values, and the time complexity being proportional to 2 to the power of 32 operations. But in this particular equation set, you can observe a phenomena that equation 2 and 3 does not depend upon 2 key bytes. And therefore, what you can do is you can essentially do a divide and conquer attack, which reduces the time complexity of the attack from 2 to the power of 32 to only 2 to the power of 30 values. So that means, right, that an attack which you were previously able to do in 1 hour, now you can do it in 15 minutes. That is almost like 1/4 speed up. So, so that essentially roughly kind of concludes our discussion here. And in particular, like recently, we essentially have tried to kind of automate this process. And this is the paper that we published at Chess, where you can essentially pretty much write down the cipher in a specific language, and the tool automatically does a data mining based approach to come up with these equations that we essentially manually derived, and then essentially find out what is the fault complexity and such complexity of these attacks. So I would just stop here for a break by like just mentioning that this attack also was prevalent in this famous attack now against Intel SGX, and this is called as Plunderbolt, which is a software-based fault injection attack which was done against the implementation of AES on Intel SGX enclaves. So Plunderbolt, actually, if you go into the methodology of the attack, it essentially tries to target some specific registers which are called as model-specific registers, and try to show that if you write negative voltages to these MSRs, then it creates undervolting of the CPUs, and that leads to making the cycle time smaller than the propagation time, which leads to the manifestation of faults. And then it shows that you can even do these fault attacks in a remote manner, and this pretty much led to the deprecation of Intel from its 11th generation processors. So the underlying attack you can see here is still the same single fault attack, and if some of you are interested, you can also look at this GitHub repository, which gives you the code for performing this fault attack. So I think I will stop here for some time and rather switch over to a practical demonstration that Siddhartha would be demonstrating here. So maybe I'll switch over to Siddhartha at this point. Siddhartha, would you like to talk?
Yeah, sure.
So let me stop sharing.
Yeah, we'll start the demonstration. Okay, so I hope my screen is visible.
Yeah.
So yeah, so I'll start the demonstration. This is regarding the single byte fault that sir already mentioned in AES. So yeah. So first, let me go through like what we are trying to do in this practical demonstration. So this is a collab window, as you can see. So in this demonstration, we will be trying to simulate a fault in the first byte of the 8th round of AES, and that, as you can see, like as demonstration in this figure, like this fault will be propagating through the rounds. Like after the 8th round, in the 9th round, it will be the fault will spread through the first column, and then after the 9th round, it is going to spread over the whole state matrix of the AES. So now, in order to exploit this, sir has already mentioned the equations that you have already seen. So this is the relation, like the equations that are present within the state matrix, they have certain relations within them. Like there is 2F1, F1, and again F1, and then 3F1. Like this is what we exploit in order to extract the 10th round key. So let's start with the simulation of the fault initially. So this is the fault simulation code that we'll be showing. So over here, as you can see, like AES is being executed in these steps, as you can see. And over here, we have already mentioned the byte location where we will be injecting the fault is 0. The round at which we will be injecting the fault is the 8th round, and we'll be targeting 2 faulty ciphertexts. Like we'll be trying to inject 2 faults. So like we have a pair of correct ciphertext and a faulty ciphertext, corresponding faulty ciphertext. So now the code has executed. So we have a pair of correct ciphertext and faulty ciphertext over here. So as now this pair of correct and faulty ciphertext will be now be exploited in order to extract the 10th round key. Now in the next part, we'll be exploiting the DFA, like the differential fault analysis, where we'll be exploiting these equations as I already mentioned. So now suppose this is my correct ciphertext, so I'll be copying it onto this part. The faulty ciphertext. Okay, so after I have just copied the correct and the faulty ciphertext, I will be now executing the DFA code. So the DFA code mostly consists of the pair of equations that just now showed. Like we'll be exploring with by guessing the fault value and the key value correspondingly. Like we'll be having 4 set of, like this is for key 1, and this is for key 0, this is key 1, key 2, and over here there is key 3, and we are testing it in a range of 0 to 256 for all the key bytes, and for the fault we are testing it from a range of 1 to 256, as we are considering a non-zero fault value over here. So this will be running on with a pair of correct and faulty ciphertext. So that's why, like, this is for the first ciphertext and this is for the second ciphertext, and then we'll be getting an intersection of keys, and out of that we'll be getting the correct 10th round key. So now let us execute the code. Yeah. So after the execution of the code, as you can see, like we have this 4 key bytes: 0x13, 0x2b, 0xS7, 0x17. Now if we verify this, like verify this part of the code, like this part of the code is actually extracting the original 10th round key from the original Aes algorithm that was being executed. So now, as you can see, like if you carefully watch, like 13 is over here, then 2b is over here. If you consider this A7 is over here, and if you consider 17, you can get 17 over here. Like all the keywords that we actually targeted, we actually obtained it. So this is a sample execution of how we can run DFA by simulating the fault. This can also be run, like if we inject a fault on an actual execution of an AES on a FPGA or maybe any other device. So this same algorithm can be used in order to extract the 10th round key. So is there any doubt regarding the execution of the code or the flow?
Okay. Any questions, comments that you would like to make at this point? Okay, so in that case, yeah, so any points to discuss here, or we can go ahead for the next parts actually. Like, is the basic idea of faults conveyed at this point, like how faults can be exploited for cryptanalysis? Okay, Siddharth, I think we can go ahead then. Okay.
Okay, so then I'll stop sharing.
Okay. Is my screen visible?
Yes, sir.
Okay, so let's come to the next part of the attack. We have a discussion where we would like to, like talk about some potential countermeasures and how they can be thwarted by advanced fault attack techniques. So in particular, like countering faults is tricky because often, like it's a kind of fight between the designers of the algorithms and also the implementers of the algorithm. And in reality, right, it is probably a fault of both. And therefore, like, when you talk about countermeasures, then both the designers and also the implementer needs to participate together. So how can countermeasures be built? So the first approaches of developing countermeasures was based on classical fault tolerance, which is by adopting redundancy to your faulty computations. So one of the, like first thoughts that probably comes to one mind is what are called as detection-based countermeasures. And these are kind of modified into certain techniques which are called as CED or concurrent error detection codes, where various kinds of redundancies are being employed to detect faults. And these are, like often vulnerable to the fault attacks itself because the very comparison step that you have can also be subjected to attacks. And, and moreover, right, they're also vulnerable to another class of attacks which are called as biased fault attacks, which I will try to talk about in the next part of my talk. So what I mean is that, like the basic idea about or on CED schemes which are based on are basically the fact that suppose you do an AES operation or maybe any ciphering operation. So this is suppose your cipher that you have implemented and there is a redundant copy of the, so let us call this as the redundant copy of the cipher that you implement. And then you do a comparison of these results. So whether these two are same and only when they are same, then you produce the output, else you kind of randomize the output or mute the output. Now, the idea is that the reason why you essentially believe that this is kind of quite difficult to counter or, like circumvent is because these ciphers, as we saw in the context of AES, has got a, like a data path or size of almost 2 to the power of 128 because there are 128 bits. Now, the probability in a situation where, like all the states are equally probable, that the two, like computations will result in the same output is 2 to the power of minus 128. And that is pretty small. But the point that probably often we miss is that this probability is under the assumption that all states are equally likely. On the other hand, when you talk about fault injections being done by malicious adversaries, then the attacker can often bias the fault injections, and that significantly increases this probability of collision. So the question is, right, does detection always guarantee security? So this is an example of an adaptation of the hardware-based redundancy, where rather than, like using the hardware and repeating the hardware, you try to kind of do the computation twice. So this is called typically as a time redundancy countermeasure. So where you have an original computation and there is a redundant computation, and if there is a mismatch, then you suppress or randomize the output. But if there is a match, then you generate the output. So now what we would try to first motivate is that the fact that the fault collision probability can significantly depend upon the bias of the fault injection. So note that there are two important controlling factors. One is the size of the fault space, and the other is the probability distribution of the faults in the fault space. And if there is a a non-uniform probability distribution of the faults, then there is a significant increase in the fault collision probability. So what I mean is that if you take a uniform fault model where all the faults are probable with the same probability, then the probability of the collision is is inversely proportional to the states of the your fault data path. That means in the case of AES, say suppose n equal to 2 to the power of 128, and therefore 1 by n is significantly small. However, if there is a bias in the fault injection, then this probability significantly increases. In order to understand that, let us try to consider this explanation. So imagine that there is a there are a total of say small n faults that are possible under some fault model. So this n is important based on the fault model, because if you assume, for example, a bit fault model, okay, bit fault model inside maybe a a state of 120 bit. In the case of AES, then since any of the bits can get faulted, your size of n is equal to 128. On the other hand, right, if you consider a byte fault model, then your n will become 2 to the power of 128. Okay, so therefore the number of total possible faults depends upon the underlying fault model. In a general case, let's consider n to be the number of possible faults which are possible under some specific fault model which you choose. And imagine that each fault, say this, is denoted as Fi, and it has a probability of Fi of occurrence. And if V is the variance of your distribution, so here are 3 situations that are shown here in this table. In the first case, this is a uniform fault distribution. You can see that there are 8 faults, all of them occur with a probability which is same. In the second case, I make it a bit more skewed. In the third case, I make it further more skewed. And you can observe that, the skewness can be observed by the variance of this distribution. And now what is the impact of this variance? You can calculate, and it is not very difficult to verify that the probability of collision, you can actually denote it as n into V plus 1 by n. So note that 1 by n was where my V was equal to 0. So in a uniform case, your V will be equal to 0, and therefore, right, you will be left with this probability of collision being 1 by n as we saw. But in a situation where V is more than 0, that means V is non-zero, you will find that this essentially has a positive impact on this fault collision probability. And therefore, for a very skewed distribution, this probability of collision can significantly increase. And that can lead to the fact that, although you had a fault, but since you had the same fault, you essentially will be in this situation where you, allow your detection mechanism to kind of, not understand that, since the faults were same in both cases, it will take this path, and therefore it will generate the output, and that will essentially result in the faulty output being observed by the adversary, and following it, right, it can do the similar attacks that we have just now seen. So now in particular, we can actually do even better. So we can try to develop specific techniques of exploiting these faults. And these are what brings us to this question of how we can exploit this bias in a different manner. Okay, and make it more practical as well. So in order to understand that, we will try to kind of define a term which is called as fault intensity. So in particular, I will take an example of a combinatorial block, which is shown here as this box, and this is a 4x4 mapping. Now, for some of you who are working on ciphers, you know that a 4x4 combinatorial block is often very popular in the context of what are called as lightweight ciphers. So if you take, for example, ciphers like present and so on, right, you will find that they have S boxes which are of dimension 4x4. You can also extend these discussions to more other parameters of the S box like 8x8 and so on. So in particular here, since there are 4 outputs, you can easily imagine that each of these output bits pass to different combinatorial circuits, and therefore they have different delays. So here is an example of a clock which is basically going to the input and the output registers of this combinatorial block. And depending upon the maximum path delay, for example, you can observe here, we see here that one of the bits gets faulted. This is the output bit, in this case shown as output bit 3, which are the largest delay. And therefore, when I do a clock glitching, that means I make the clock faster. This is the line that is going to fail at the first point. Okay. And now what does that indicate? It indicates that although, right, I would have assumed in a random fault injection that all the faults or all the bits had an equal probability of getting faulted, but because of the underlying physics, this is not random process, and therefore this particular bit, in this case output bit 3, is the one that will get faulted at the beginning. And this shows that every time I repeat this process, this output bit 3 will be the first one which will fail. And if I make the clock even faster, then output bit 2 will get faulted and so on. And therefore, right, with the more I make my intensity higher, I would say that my, more bits will get affected. So this essentially was shown in this paper in FDTC 2014 by Patrick Schumont and team, which is called as DFIA, or Differential Fault Intensity Analysis. So we'll try to see how we can utilize this and exploit them. In particular, DFIA tries to combine fault injection and principles from side channels, which are called as differential power attacks, and tries to kind of, exploit and, indeed, obtain the secret keys, in a very interesting fashion. So in particular, what it does is, if I just compare the DFA that we saw just before, in the context of DFA, you had taken a plain text, you had obtained a correct cipher. You had taken the same plain text and you had obtained a faulty cipher, and you had used both of them to get the secret key. Now in a DFIA, what you do is that you don't at all require any correct cipher. What you can do is you can take the plain text and you obtain different faulty ciphers. Okay, so you essentially create various faults and you obtain a bag of faulty ciphers, and you analyze this bag of faulty ciphers to give you the key. So you do not have any requirement of getting a correct cipher, to do the attack. So how does this work? So what you do is, the first step is, of course, to do a biased fault injection. So in this case, if I take this 4x4 example, I do a clock glitching and I do a biased fault injection. Imagine that I do a clock glitching in a manner so that only one bit flips. For example, here I can control the intensity by making the clock glitch such that only this line, for example, gets faulted. And that way, right, I can control the intensity of the fault. And therefore, if I make the clock operate at this frequency, then I would expect that since only one bit will get flipped, therefore, right, if I take, for example, one snapshot of these 4 bits and I compare with another snapshot of these 4 bits, then the only bit that will be different is this bit, whereas the other ones will remain the same. So now we try to kind of apply this to perform this attack. So what I do is I inject a fault at this point, and I know that the differences here are only restricted to few bits and it doesn't propagate to more bits because I control the intensity of the fault attack in that manner. Now, how do I use this fact to distinguish the correct key from the wrong keys? So I make a guess of my key. Suppose I start with this guess being 0. So note that I'm guessing only one nibble of the key and I'm doing it in a divide and conquer manner. And there are total 16 possible values of this key. So I denote them as by 0 to 15. So let me start with the key nibble being 0. And I therefore, I get the faulty nibbles and I XOR it and I perform the inverse S box and I come to this point. And I note that what I do is that I started with a bag of faulty ciphertext here, and therefore I have a bag of expected states at this point, which are dependent upon this key hypothesis that I made, which is 0. And now I start calculating the differences between these state values. So now I note that because of the intensity, the number of bits which are getting different are only 1 or maybe very small. And therefore, if I calculate a sigma of these Hamming distances, which are shown here, I would expect that this summation would be the minimum, for my correct key. So what I do is I take these values and I kind of, start guessing all these 0 to 15 values. So I don't note them as say 0 to 15 values. And I correspondingly find out the Hamming, this term, say row 0, row 1, and so on till row 50. And out of all these possible values, I choose the one which has got the minimum value. And that essentially is my expected value of the key hypothesis, because I know that for incorrect guesses, I will probably get a larger value because that essentially doesn't adhere to my computation. So this way I can try to, distinguish the correct key guesses from the wrong key ones. So note that this is a divide and conquer algorithm. Therefore, right, even if you increase the key length, these attacks cannot be stopped. So therefore, right, we have a mechanism of doing a bias fault injection. We have a mechanism of also circumventing them. And because of this, right, even if you have a detection-based countermeasure, they will be vulnerable against bias fault injection. So finally, I come to some quick discussions about modern times of fault attacks, where I will try to give a quick overview behind two attacks, which essentially are called as Statistical Ineffective Fault Attacks, or SIFA, and fault template attacks. So ineffective fault attacks essentially, or faults essentially, are a very interesting class of fault injections. So in the previous cases, remember that our mechanism of doing fault injection countermeasures was to kind of having a mechanism so that it understands that there is a fault, and if there is a fault, then the fault is not exposed to the attacker. And we believe that such faults essentially are fine. And so the idea is that if there is a fault and that is being screened by your countermeasure, that is not exposed to the adversary, it should be fine so far as your security leakage is concerned. However, ineffective faults shows that even if the fault is ineffective, which means that you induce a fault and that doesn't really result in your corruption of the cipher text, even then those faults can leak. So in order to understand this, let us take a very simple example of a very common fault model, which is called as stuck at zero. Okay, so stuck at zero means that if you have a VLSI circuit and you inject a stuck at zero fault, which means that that particular line gets stuck to zero. So likewise, you can have a stuck at one model as well. So if you consider a stuck at zero model and imagine that no corruption occurs, that means you inject a fault and you find that even in spite of the fact that you get the correct cipher, then that immediately tells us that the bit at which you are injecting the fault, the correct value of that bit is actually zero. And that is why, right, although you had a stuck at zero fault, it did not corrupt the output. On the other hand, right, if the, if you get, the output is one, then output is faulty, then that indicates that that corresponding value is one. And therefore, right, this shows that when you have got such kind of fault injections, then an ineffective fault can also reveal information about your internal states. So these class of faults, in the former case, for example, when no corruption occurred, okay, because in spite of the fault, essentially is an example of what we called as ineffective faults. So now in this kind of in this paper, in this work, which essentially is called as SIFA, attackers showed how you can extend it to what are called as statistical ineffective fault analysis. Now note that when you talk about stuck at zero fault, right, one may argue that such kind of faults are not very common. So therefore, right, the idea of these attacks is to extend it to some statistical nature, which are called as SIFA, or statistical ineffective fault analysis. So in this case, let us, in order to understand this not so intuitive intuition, let us take a 4-bit state, okay, some intermediate state, and we know that there are 16 possible values of these 4-bit states. And out of this, imagine that the MSB is, faulted by, again, my stuck at zero fault model. And I note that then it is kind of quite easy to understand that in that case, the first 8 values will all result in ineffective faults because they correspond to the cases where the MSB essentially has got 0 values. And therefore, the stuck at zero fault will not be effective. And therefore, they will all be of ineffective nature. On the other hand, if you take the situations where the MSB is 1, they will be effective faults because they will corrupt the output and so on. So now the interesting idea is that what is the impact of this on bias? So note, we already discussed about how to exploit biases in, in order to understand and distinguish the correct key from the wrong ones. So we will try to see how, what is the effect of this on the bias. So in particular, note that if this was an internal state of a cipher, then they can take, all of these states will take probably equal probability because, in a cipher which is well designed, the states will have equal probability. Okay, they will be uniformly distributed. On the other hand, if you consider the state of ineffective faults, you note that only the, these values essentially corresponded to ineffective faults. So therefore, if you kind of restrict your analysis to only ineffective faults, you will find out that ineffective faults will occur all with the same probability. But the other ones, for example, in this case from 8 to 15 will never occur. And therefore, they will have a probability of occurrence of 0. And therefore, because of this, you will get a biased distribution. Okay, as you can see here that this distribution is biased towards the value from 0 to 7. So now, once you have this bias by the techniques that we have seen previously, like DFIA and so on, you can essentially exploit them and you can distinguish the correct keys from the wrong keys. So this is a very high level kind of, like overview behind SIFA. And this essentially is a very powerful attack because even if you have countermeasures, you can essentially exploit them and you can essentially recover the secret key. So this idea was published in Chess in 2018, which shows how you can exploit ineffective fault injections on symmetric key crypto. In particular, this attack was also applied on masking, which is essentially a very popularly known side channel analysis countermeasure, and shows that even such countermeasures are not able to kind of thwart this powerful class of attacks. So I would rather not go in details into this. If you're interested, then I would point out to this AsiaCrypt 2018 paper, where it was shown how SIFA is applicable on masked AES implementations. Rather, I will try to kind of conclude our discussions by quick discussion about what is called a fault template attacks. So fault template attacks are, like essentially the first example of how template attacks can also be done on, by exploiting faults. So by template, I mean that I've got, like a target device. And if I want to perform a fault attack on this target device, I go to the market and I buy a similar device, which I use to build my template. Now, on this template device, I essentially induce various kinds of faults, and I observe the fact that whether the fault propagates to the output. So in certain cases, the faults will propagate, which I indicate as 1. In certain cases, the faults will not propagate, and I indicate that as 0. Now, using these fault templates, now when I want to do an attack on the target, I inject similar faults, and I again observe the template essentially, which is given by the fact whether the fault propagates to the output or not. And then I use my previously obtained template, and from there, I essentially try to recover the secret key. So this is a very top level idea about what essentially fault template attacks would try to do. And the reason why they work is essentially shown by this illustration. So I show you, say, 2 important gates. Let's concentrate on the AND gate, for example, and try to understand why the fault templates depend upon data. For example, imagine that this is an AND gate. It has got 2 inputs, A and B, and I inject a fault in one of the inputs, say A. And now I observe the fact whether the fault propagates to the output or not. Note that the fault will propagate to the output. I mean, for example, if the fault will propagate to the output, you see, then that leaks information about one of the bits. For example, you know that if this bit is 1, then the fault essentially will propagate to the output, else not. So this data dependence of fault propagating to the output essentially is the basis on which fault template attacks are devised. And this can be a very powerful class of attack because it can also target middle rounds of a cipher, and it can work without any plain text ciphertext access. You just need the fact that whether the fault essentially propagates to the output or not. So therefore, these attacks or these class of attacks essentially has got 2 phases. In the first place, you have got an offline template building phase where you have got a full access to a device similar to your target. You know the key and you know the mask. So in this case, mask is an additional level of countermeasure that you have. And you inject various faults and you create the template. The template basically, is nothing but, storing some intermediate state of your cipher. And then in the actual online phase, you again inject the device, which is on your target. You inject faults at some predefined location, and then you extract the secret by using your template that you had built previously. So this essentially has been used in, to attacks various algorithms. For example, this is an example of a S-box of a present S-box. As I mentioned, is a 4x4 S-box. And imagine that I induce a fault at one of these bits, and I indicate, and whether the fault propagates to the output or not is indicated by this event called FL0. And likewise, I inject a fault at various locations, okay, and call it as FL0, FL1, FL2, and FL3. And using this fact, whether the fault propagates to the output or not, I create a template. And now, once this template is created, I essentially can store them down as a nice table. And you can see here that by this black box, I indicate that the fault has occurred, and by the gray one, the fault has not occurred. And you can observe that the entire state, which is essentially, 2 to the power of 4, which means 16 values, has all been, as uniquely been decomposed into a template. So you can see that each of these states has got a unique template, which you can use during your template attack phase. So this essentially is a very powerful class of attacks because you can also break masking. So by masking, I mean that what you do is, this is a very popular countermeasure for side channel attacks. So where suppose you want to implement, say, X into Y, you don't multiply them directly, but rather you kind of decompose X into its mask. Say I denote it as X0 and X1 so that the XOR of X0 and X1 is X, and likewise Y will be denoted as Y0 XOR with Y1. And then I essentially perform a computation so that X and Y never participates in a computation. So here is an example of a masked AND gate. You can see here that X0 and Y0 participates in a computation, and likewise there are other shares that participates in the computation, but all of them never takes part in the computation. Now, on a quick thought, you can see here that if I inject a fault, say in X0, so for example, here is shown by this red line, and likewise here, the very fact that whether Q gets corrupted, that means the output gets corrupted, is obtained by taking the XOR of Q0 and Q1. And you can note that when Q will get faulted is only in the situation where the XOR of Y0 and Y1, which is essentially shown here, that is equal to Y is equal to 1. So therefore, the very fact that whether the fault affects the output essentially leads to an, like effective, I would say like merging of the shares of Y, and that leads to the leakage of one of the input bits. And likewise, right, if the output is correct, you can also infer that Y was equal to 0. Okay, so this is a very simple example to illustrate that why fault template attacks can be a powerful attack vector to even like compromise like various kinds of ciphering algorithms. So I have come to the final part of my talk. I mean, if there are any quick questions till this point, I would be happy to address. So I will stop for a while to see if there are any questions till this point. Okay, so I'll go ahead to the final part, which is essentially on the leakage assessment of faults. So leakage assessment means that now suppose imagine that I have got a device, and imagine that we have got several kinds of block ciphers, several kinds of attacks, and like although several countermeasures have been built, many of them have been also broken. So the question is, right, how do you judge which one is secure and which one is not? And if you go to any designer of a countermeasure, they will be often very reluctant to give you all information about what really happens inside their systems. And this means that we need to kind of devise techniques to understand and like analyze whether the faults are really leaky or whether they are not leaky. So we had a like work in that 2019 where we try to kind of come up with a framework which we called as ALAFA, or automatic leakage assessment because of faults. So the idea being very simple. I mean, what we do is we do a fault model. So we have got a your favorite fault model, say a Byte fault model, considered is the protected cipher of AES. And what you do is you take two fault values from its sample, say F1 and F2, and then you perform like a simulation of the cipher. So note that once you obtain like a simulation, here you have got, say, this simulation is denoted as tau F1, and likewise if you take the fault value as F2, you have got another fault distribution denoted as tau F2. And you then perform a statistical t-test to distinguish between these two distributions. If these two distributions are distinguishable, then that implies that by the theory of non-interference, that means that from the cipher, you can essentially obtain information about the faults. Now, one can argue that the fault is not the secret, but the secret keys. But you can essentially show, and we show this in this paper, that both of them are equivalent. That means the secret key is, of course, the secret, but the fault is also an equivalent secret information. If one obtains information about the fault, then it can also similarly obtain information about the secret key. And therefore, right, if the output cipher has got information about the fault, then that means that it is also leaking information about the secret key. So by this argument, you can essentially develop a very interesting, framework for, fault leakage assessment, which is kind of similar to a very well accepted side channel leakage assessment, which is popularly called as test vector leakage assessment, or TVLM. But of course, it has to be adapted in the context of faults, which is not often very straightforward. It is simulation based. It is also algorithmic agnostic. That means you can run it for AES, it can run it for various other ciphers as well. So now we would like to, give a little bit of overview behind this, and you can essentially use this to analyze various kinds of leakages like DFA or like SFA or SIFA. And the idea is that essentially what we are trying to do is we are trying to kind of model the differential of the cipher as a function of like not only the plain text and the key, but also on the fault. So that is essentially the unique kind of, I would say, like takeaway of this leakage assessment framework. So now what you do is basically you take this observe. So this is the output observable, and it's basically a complicated function which we called as the leakage function, which depends upon the plain text and the key and also the fault value under the specific model. So now the question is, right, I mean, what I mentioned is that leaking the secrets here, of course, are the key, but also the fault value is the secret. And leaking the exact value of the fault has got the same effect as leaking the secret key. So therefore, the condition of like mutual information or condition for no leakage can be observed by this mutual information between the differential of the cipher and the fault value and the differential of the cipher and the key. And that essentially leads us to this definition of analysis. So what we do here is we keep the plain text fixed throughout the analysis. And we essentially want to kind of evaluate that whether like the output differential essentially has got an impact of the corresponding fault. And in order to study that, we take different values of the fault and we see that whether the corresponding differential of the cipher has got a distinguishable impact because of the choice of the fault values. And that is precisely done in this analysis, and as shown over here. And you can see that you can essentially very much kind of utilize this in your like framework. So this is basically based on non-interference theory, which is often a very popular technique that is used in probabilistic program checking. And the idea being that if there is a probabilistic program and you essentially take different values of the different inputs and you label them as like low if they are public information and high if they are sensitive, and see the output observables. If the output observables are distinguishable, then that means the like the different values of the high that you are choosing or the secret values that you are choosing, they have a visible impact on the output observable. So this is very easy to verify, and often equality of the distributions can be justified in many ways. And in our case, we take t-test as an example. So t-test essentially is a very popular technique that is often used in side channel analysis also. And we kind of adapt this in this context of fault analysis. So in particular, we also try to kind of develop a deep learning based framework for doing this analysis. So here is a quick illustration of how it works. So what we do is we take the encryption, we subject it to different values of faults, so call it as F0 and F1. And then we take this database and we use this database to train some machine learning architecture. So in our case, we take a deep learning architecture and we try to see that whether this machine is able to understand that whether the fault was F0 or whether the fault was F1. So note that in a random case, this will be able to do it with a probability of 0.5. And therefore, we try to see that if the validation accuracy varies from 0.5. If there is a little bit of increase over 0.5, then we believe that the output differential essentially is leaking information about the faults. So using this, we have analyzed several, a plethora of countermeasures. Like here, you can see some detection countermeasures, and then there's some complicated countermeasures called as infective countermeasures. All of them essentially are able to kind of, like showing that there is a potential leakage because of the faults. And this shows the, the efficacy of this method of adapting deep learning for fault leakage assessment. So this brings me to the end of my talk. I mean, I would like to conclude with these few comments that faults can be catastrophic for ciphered implementations. DFA or differential fault analysis works by combining differential cryptanalysis with faults. A random 1-byte fault at the input of 8th round of AES can reduce the key size drastically. And in fact, what we discussed is that 2 such fault injections can uniquely give the key. In fact, what we had discussed is that with a single fault injection, you can reduce the key size of AES to only 2 to the power of 8 values with the time complexity proportional to 2 to the power of 30 AES computation. And this was one of the attacks that was used with respect to Plunderbolt for attacking the Intel SGX platform, and shows how even like they are prevalent on practical systems in the modern day. We also discussed about how biased fault injections can be utilized by a technique called as DFIA or differential fault intensity attack. And we also discussed about some very recent fault analysis techniques, namely SIFA and fault template attacks. And we believe that there are exciting, like prospects on fault analysis research, countermeasure designs, validations, and testing. So here is a textbook that you can, that we have referred to for fault analysis and fault our discussion. So you can take a look at these books published with CRC and Springer. There is also an online course on hardware security with which we run with more details about these techniques. So with this, I would like to say thank you for your attention. I mean, I believe that this course was of utility to you. And if there are any further questions that you would like to drop to us, please feel free to contact us to my Gmail or my official email at computerscienceandengineering@IIT Kharagpur. So with this, I would like to also thank my co-speaker Siddhartha for this demonstration. If there are any further questions, I would be very happy to address. So thank you, Leonidas, for your comment. Okay, so I don't see at this point there are any questions. If not, then I would like to hand over to the organizers. Thanks to all of you.
Thank you.
Thank you. Bye.
Bye.
By the way, can I also obtain a recording of this class?
Yes, the video, the recording video will be uploaded to a Google Drive.
Yeah.
I think it will released after the conference.
Okay, that would be very helpful. Yeah.
Yep.
Okay. Thank you.
Okay. Thank you.
Bye.
Bye.
Bye. Bye.